first of all, I'd like to thank the organizers for this opportunity to give a talk here. And my talk will be, in some sense, a review of certain results known in the sphere. And let me start with the following simple notion, which implies the importance of these problems. If one considers a particle on a two-dimensional surface with initial position, initial velocity, then it is well known that with no external forces, it will be moving right along geodesics. Of course, if we add some certain initial field, then the motion will be more complicated. And such systems are called natural mechanical systems. It is a triple of a manifold configuration space. The kinetic energy T is just a remaining metric on the surface, and the potential V. In appropriate coordinates, its dynamics can be described by equations, by Hamiltonian equations of form 1. Let me remind you some definitions. An arbitrary function of cotangent bundle f is called the first integral of the system if it conserves along trajectories of our system. And the key definition here is the following one. Hamiltonian systems with n degrees of freedom are called completely integrable systems, or integrable in the sense of UV, if they have exactly n first integrals which are functionally dependent almost everywhere and are inverse in evolution. Of course, one of these integrals is Hamiltonian, and in our case, when we consider mechanical systems on two-dimensional surfaces, we need just one more first integral to reach the complete integrability. It turns out that there are some logical abstractions to this property, and the first theorem, this is the theorem obtained by Valery Vasilyevich Kozlov, and it states that if our configurational space is neither a sphere nor a two-torus, then such system defined on this surface is not integrable. So it is. We may restrict ourselves to just only sphere and torus, and let us consider the Hamiltonian system with Hamiltonian of such a form. Means that our metric is Euclidean, and our system is defined on a two-torus. V is a potential, and it is assumed to be periodic functions with certain lattice periods. And what is known here? It is known that if V is of the form 1 or of the form 2, then there exists an additional first integral, which is either linear in momenta, or quadratic. An n-degree polynomial in momenta first integral we will call irreducible if it is independent on Hamiltonian, and there is no other first integral which is also independent on Hamiltonian. And it turns out that if one considers an arbitrary system in nature, then its first integrals are either polynomials in momenta or functions of such polynomials. So it is natural to restrict ourselves only on class of polynomial integrals when studying the problem of integrability of any system. And there is a hypothesis firstly given by Kozlov, then that states that in case of two-dimensional torus, actually these two cases, which was described above, these are the only cases when there exists an additional first integral analytical of the first or of the second degree, and it is just a hypothesis and it is not proved yet, but what is known so far? The case of an integral of third degree is already proved. Michael Bialy proved this case only for potential with orthogonal lattice. So he proved that if there is a polynomial in momenta first integral of third degree, then there exists a polynomial, a linear first integral which is independent on Hamiltonian. Kozlov and Denisov generalized this result in the general case, and as to the fourth degree, certain results were obtained by the speaker, and finally, a couple of years ago, Kozlov and Denisova proved that there are no irreducible integrals of the fourth degree. It means that the hypothesis of Kozlov holds in these two cases for integrals of third and fourth degree. As to the fifth degree, Andrei Evgenievich Mironov proved this hypothesis, proved that this hypothesis holds always, but some special cases of the potential, and in which cases it is still not clear if it is true or not. Okay. Let me skip this slide. It is well known that with that geodesic flows are tightly related to natural mechanical systems, namely via Novosibirsk principle, one can construct, having a natural mechanical system, one can construct a new Hamiltonian, and if the initial mechanical system was integrable at least on one energy level, then we may take these results and generalize it on the case of geodesic flows. Geodesic flow on its own is much more complicated object to study, and almost nothing is known about this object. This is the definition. And the question now is as follows. Which metrics exist on a two-torus for which the, or maybe not on a torus, but on an arbitrary surface, for which the geodesic flow is integrable. And we will restrict ourselves only on the case of two-dimensional torus, and that there are known metrics, for example this, the first one or the second one, and in these cases there exists either linear or quadratic first integral in momenta. And the hypothesis by Kozlov of course states just the same in the case of geodesic flows. And there are no such results for geodesic flows in the case of third degree integral or fourth degree integral. It is still unknown if this hypothesis holds or not. And what is known? Bialy and Mironov proved that if the Hamiltonian system has the first integral of an arbitrary degree n, then there exists globally the geodesic coordinates. Magic has the following form, the Hamiltonian, and we may find, we may search for the first integral f in such a form. And moreover, the condition that f is the first integral is equivalent to the following quasi-linear partial derivative equation system. And it turns out that such systems has many beautiful properties. Namely, this system is semi-Hamiltonian system. Semi-Hamiltonian systems were introduced by Sergey Agapov in 1985, and they are studied extensively so far. And a system, if the system is semi-Hamiltonian, that means that it can be written in the form of conservation laws, and moreover, in hyperbolic domain, they possess remaining invariance.
What is hyperbolic domain?
When all the eigenvalues are of our metrics are distinct and pairwise, really pairwise distinct. If we will be working in conformal coordinates, then the metric has the following form, and the first integral looks like this. It is known that if conformal factor is a trigonometric polynomial, then there is no irreducible integrals. It was proved by Kozlov and Denisov. Moreover, there are some conditions in view of Koltsov's theorem on the coefficients of the first integral. And again, the condition that f the first integral is equivalent to existence of smooth periodic solutions of a certain quasi-linear system, partial derivative equation system. And the same authors proved that in this case the system is also semi-Hamiltonian. The initial definition given by Tsarov of such system is as follows: that the following conditions on its eigenvalues must hold, and it can be treated like existence of a diagonal metric with such symbol Christoffel symbol. If rotation coefficients of a metric are symmetric, then such metric is called Egorov metrics. And there is an interesting relationship between the notion of semi-Hamiltonian systems and the condition for corresponding metrics to be Egorov 1. Namely, Pavlov and Tsarov proved the following theorem: that if the semi-Hamiltonian system have two conservation laws of special form, then corresponding matrix is Egorov matrix. And Mironov and Bialy proved that our system, in the previous slide, which is written, is a Egorov system. And this is all about standard geodesic flow. So this question is complicated and is not clear what one can do. But one may consider the following problem. The problem of integrability of geodesic flow in magnetic field. The Poisson bracket in this case looks like this. Our momentas are not convergent anymore in respect to Poisson bracket. And it turns out that the condition of integrability of geodesic flow on all energy levels is very restrictive. It is rather natural because if we change the full energy in magnetic case, then dynamics changes a lot. There is the only example known with integrability on all energy levels, and in this case there exists a linear in moment, the first integral. And it seems that there are no other examples. So it's natural to consider integrability at least on fixed energy level. So we fix Hamiltonian equal to 1/2, and then we may parameterize momentum by the following way. And making some simple calculations, we obtain a partial derivation equation system on coefficients of the first integral on magnetic field, which can be eliminated from the system. And again, the question is reduced to the question of existence of any smooth periodic solutions of such a system. The system is very large, and for example, in case of n equal to 2, that's how it can be written explicitly. And by the same authors, Bialik and Mirov, it was proved that this system is semi-Hamiltonian. They also proved that it is a Yegorov system in the case of n equal to 2 or 3. It means that there exists an additional first integral of degree 2 or 3. And the speaker generalized this result on the case of arbitrary n, namely if the magnetic geodesic flow has an additional first integral of an arbitrary degree n on a fixed energy level, then the corresponding semi-Hamiltonian system has two conservation laws of such a form. And via Tsarov-Pavlov theorem, it means that the system is of Yegorov type. So I guess that was all I'd like to tell you about it. Thank you.
That magnetic field represented by omega should be quite arbitrary, or is there some restriction on the form of the...
No. As I know, there are no restrictions.
The previous, maybe
This
here,
one.
omega, just
arbitrary function.
Just function.
Any more questions?
I will just see one of the previous title, geodesics flows on two-torus.
Yeah.
No. Page with next.
This one.
Yes.
This is just one definition of geodesic flow.
Why F defines like this from TSR T2 to...
Because this is the arbitrary function of coordinates x and momentus p. For example,
систему на коэффициенты, полиномиальный интеграл полностью удалось решить, да? Для любого тайма. Самый последний.
This one?
Да, вот это. Он удалось принадлежит. Ну, доказательство в этом было, что...
What do you mean? Sorry.
For any n.
Ну, вам удалось проинтегрировать эту систему?
Нет, в явном виде нам не удалось интегрировать. Это не система, это просто идет по закону сохранения. То есть,
Ну да,
this one. Нет, явных решений не было построено. А законы сохранения были найдены из других соображений. Мы работали вот.
То есть,
Вот с этим.
надо зачем найти закон сохранения,
Ну, чтобы доказать, что она егоровская, в силу теорем Павла Царя.
Any other questions?
And in all these settings, you consider only analytical.
Yeah, sure.
So, are there some explicit examples with only smooth? That are only smooth. There is some explicit, well-known difference between analytical and smooth situation.
As to magnetic geodesic or for example, as to the natural mechanical systems, if I remember correctly, the fourth degree is Kozlov and Denisov proved that there are no C3 smooth solutions of the corresponding equations. So yes, there are questions related to smoothness for analytical. That's not the same.
If there are no questions, let's thank the speaker again.